Right, recording is rolling. Welcome to Thursday. Ooh, we're getting pretty close to the end of another week here. So last couple of days we've been doing reflection. We did some ray diagrams for looking at concave and convex mirrors. We're going to switch over and look at refraction today. Before getting going too far on that, we got top scientists for the quiz you guys just turned in a couple days back. So if your name's up here, then awesome job. Look at all these top scientists. You guys are doing so awesome. Now, I do have the solutions written and ready to go, and I want to get you guys these quizzes back as soon as I can, but there are, I'm still waiting for a bunch of quizzes to come in. So if you haven't turned your quiz in yet, then please do turn that in soon so that your classmates can get their quizzes back and get the solutions too. And so agenda today, a bunch of refraction related activities. So let's see. We're gonna say like, here. See, look at this laser pointer, do a quick demo. Right? I got this, hey, look at this. You see those words all up in wonky there? Right? Shine the laser through, oh, the light bends. Right? Now, why does it bend? Could you figure out, to quantify and what angle does it bend relative to something? And does it have something to do with like, what if this was a different material? Would it bend more or less? Okay? So I'm gonna switch the screen over. Okay, and have Paul Hewitt introduce this idea. Nope, this one.
Inclined plane.
Pause real fast. Got some pictures. Okay, so got a straw. You see a straw bent inside the water. That's an example also of refraction. I have an animation for you guys real fast. Animation. Ooh, look at that. Got an inverted image. Yay, back to Paul.
And I got some wheels. And I'm just going to roll the wheels down the inclined plane. Okay. What I'm going to do is I'm going to roll the wheels from a nice smooth sidewalk onto a rough piece of material. It's almost like wheels rolling along a sidewalk into the grass, or light coming down and interacting with the material and slowing down. If I roll them at an angle, did you see it bend? It came down like this and then bent. Let me put that on the board. My wheels are coming down in this direction, and they're coming from the smooth surface to the rough surface. When the wheels get to the rough surface, what happens to the speed of the wheels? Slow down. You know why they slow down? Because there's an interaction with the wheel and the material. Let's suppose it's like the little pieces of cloth on the towel, or maybe it's like blades of grass on a lawn, okay? There'd be some interaction, so this part would slow down. But what happens to this other part over here? It continues going quickly. So what happens, it sort of kilters. And so what happens is it goes like this. When both wheels get in there, they're going the same speed and they continue at a straight line. So there's no mystery as to why the wheels will kind of bend over, is there? I mean, if you move along like that, something's on the way, won't your arm go like this? I mean, part of it slowed. Well, guess what behaves the same way? Light waves. When waves of light come from above, say hit water. Maybe the waves of light are coming from the sun, something like that. We got a ray coming down like that. Incidentally, it turns out a light ray and the wave fronts that represents, these are like the crests of waves. Think of water waves, yeah? Right angle in their game. Always a right angle. See, even the axis of a wheel and the direction in which it's traveling, right angle. See? So what happens over here? These waves of light come down, and when they hit the water, what happens to the speed of the waves? Oh, you don't know that? Well, check your neighbor. I mean, they somehow go faster. What's the answer, gang? They slow down. Okay, the waves slow down. So what happens? They bend, and they sort of bend like this. And they get closer together. So the wavelength gets a little less in here, but the frequency of the wave stays the same.
All right, so hold on to that idea, that model there. Once you see this a couple times, he did it once. I'm gonna draw that in the notes myself and then go back and elaborate on that a little bit. And that's gonna lead to Snell's law. Right. He's got a story here that involves refraction of sound. I know you just did refraction of light. Refraction is just like some wave that bends, right, as it changes across different materials. the story has is he used to be a Boy Scout who was in, say, like some camp here with his buddies, and then there'd be like another scout troop over here across a lake. There's this lake between them, a bunch of water. And during the day, they're yelling back and forth, and like, "Hey, how you doing?" They can barely hear each other, right? But at night, they can hear each other like whispering in their tents. Now, why is that? That across, say, a lake, you can hear very clearly what somebody's saying on the other side at night. Well, so it's something to do with refraction. We've got this. Okay, so say during the day, you say like, "Hey," you send out the sound waves. You got press, press, press. So the sound should travel about, same speed in all directions. You got all these like rays of like sound going. So it's all spread out, and only a little bit gets to the other camp. Okay? But at night, sometimes there's this temperature inversion where you have cold water and warm air above that. And if you have different temperatures, you guys remember how sound travels at different speeds and different temperatures? It travels a little bit faster in warm air than cold air. So maybe it goes out that far, as in the cool air it only goes like that far. So isn't that gonna like bend those wavefronts kind of like that? And then the like the sound rate, it all gets directed into the other camp across the water, right? And that bending is called refraction. Right? So there's a sound example of refraction. The example I showed like a light example of refraction. And we'll switch back over to these notes, right? And redraw that model that you just did, and go back and show you guys. I was going to link to something, or actually, right before I do that, so something to do with light changing speed causes it to bend, right? And we're about to make that connection. But how much would light slow down? Because maybe it slows down differently in this material compared to water, compared to like olive oil or glass or different kinds of plastic. How can you quantify that? And the way you quantify that is with something called the index of refraction. So the index of refraction is equal to a ratio of speed of, but we'll just go light, speed of light in a vacuum compared to speed of light inside some material like this right here, inside the material, which of course is different for different materials. The whole idea of like speed of light being 3 × 10⁸ meters per second, that's really only true in a vacuum, and then it'll be like a little bit slower in here as the light is like interacting with the molecules that make up this piece. Right, so this whole definition sort of way of writing this, I can write this in terms of variables like this. N for index of refraction is equal to C over V. You guys remember C is like the pure speed of light in a vacuum. C, by the way, is equal to 3.0 times 10⁸ meters per second, called a cosmic speed limit. That's as fast as you can move through space. Well, anything with mass can never reach that number for reasons we'll look at in a couple weeks. Anything that's massless, including EM waves, always have to be moving this speed through space. Right, so let's look at what could different indices of refraction be for different materials. I've found a whole table of these, so let's look at a few of them. Could be for a vacuum. What could index of refraction be for air? Let's say on Earth, like mostly nitrogen, some oxygen, the other gases, air. What's index of refraction for water? Could be a good one to know. Okay. I might put glass on this list, but there's different kinds of glass that have different indices of refraction. How about diamond? That sounds like a pretty fun one. Diamond. Okay. Yeah, anything that's transparent will have some associated index of refraction. So I bet you guys can figure out what the first one is for a vacuum. Who can figure it out? Navigate this equation. See, we got the pure speed of light, 3 × 10⁸ meters per second. Speed of light in a vacuum would also be the same number, wouldn't it? What's anything divided by itself? 1 exactly, 1.0. Okay. That's sort of like a maybe like a boundary condition on what index of refraction could even be, right? So 1.0 is like, how about through air? Now, if it slows down a little bit, wouldn't this denominator be a little bit smaller than this numerator? Okay. And if that's true, is this ratio going to be a little bit more or a little bit less than 1? It's got to be 1. A little bit more. Like that's the only way this can go. Here's the actual number for it. It's like 1.0003. Okay. Now that's extremely close to 1. So does light really slow down or refract in air? Maybe a tiny bit, hardly Later on, when we do this lab, I'm gonna call index refraction of air just equal to 1, because basically is. What about for water? It's like this, 1.333. That's why throw a straw in a glass of water, it bends significantly, or look at something in the bottom of a pool or something like that. And what about for a diamond? Diamond is like 2.42. Ooh. In fact, if you know this material property, this might be a way to test if something diamond or some other kind of material, right? Have a laser and test it out with Snell's law and get a refractive index of about 2.4. It's probably diamond. So what is the Snell's law? I keep referring to though. So let's go to Paul Hewitt's. So remember, index of refraction tells you something about how much light slows down inside some material. We got these different ratios. So go back to Paul Hewitt's model of a ray of light refracting. Again, I want you guys to see this a couple of times. So put that as information. And so we've got maybe like air versus water, for example, air versus water. Or maybe you could do air versus glass or vacuum versus glass, two different transparent materials. And then have a ray of light coming in like this. It's gonna hit the surface and slow down when it gets into the water. And for some reason, it's going to cause it to bend. And that's what I'm going to try to explain here. Is like, why does it bend? How can we even quantify how much it bends? Why would it bend? So many questions. So do you guys remember back when we were doing law of reflection, we were measuring angles with respect to a normal line, normal meaning perpendicular. Same story here. So when I eventually write Snell's law, which is going to be an equation, it's going to involve some angles because we're trying to quantify how much does something bend. Okay? The angles we're going to measure are with respect to this line that's perpendicular to this surface exchange, these surfaces. And so I'm going to call this angle of incidence, theta sub I, and I'll call this the angle of refraction, theta sub R. Okay? Or if you call theta 1, theta 2. I mean, it might be, maybe there's a light shining from down underneath the water and it refracts this way. The light could be going either way. It would look identical, whether it's going top down or bottom up. It's going to refract the same. Okay. Now, Paul here was drawing something about like wave fronts. So you draw these that were supposedly like perpendicular to the incident, right? Perpendicular to the rays. Right? I'll show you what that is and what that means. So you got all these wave fronts, front, 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 and maybe these continue on down the other way too. Okay. Front, front, front. You just keep on, right? Okay. So see how they're like equally spaced, right? Now those might represent like the crest of waves. So there's like crest, 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 and so on. Remember that light is a transverse wave, right? Light's a transverse wave. So this ray that I drew is really like a transverse wave. That's the direction light is going, that light beam. Okay? And then these wave fronts that are perpendicular to that that beam represent, say, like the crest of waves. Okay? Now, there is some frequency that these wave crests are leaving the air. See all these dots I just did? Right. Dot, 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 dot. There's some frequency those crests are leaving the air, and also some frequency that the crests are entering the water. But doesn't that frequency have to necessarily be the same? Right? So the frequency has to be the same, either on the side of the air or the side of the water. Do you guys remember this equation? This wave equation: speed of a wave is equal to wavelength times frequency. You guys remember that? Okay. Well, if the frequency of waves leaving the air is equal to the frequency of waves entering the water, that means that this equation is the same on both sides. In each material, the frequency is the same. Okay? But the speed is different. Right? Speed slows down going from air to water. So to balance this equation, what does wavelength also have to do? Get smaller. Okay? There's a direct relationship between speed and wavelength. Guess that for some constant frequency. Okay? So let me go back and fill in the rest of this picture. So picking up from those wave crests entering the water, draw wave fronts parallel to this refracted beam. I mean, it does refract, sort of working back from the solution. I see this, but so this whole picture is going to be self-consistent. We're trying to construct the story from a little bit different point of view. Okay. Guess what just happened? Right? Look at what the wavelength used to be for the air. Here's the wavelength in the air, crust to crust. Call it like lambda air, right? Wavelength in the air. Here's the wavelength inside the water. Call that lambda water. But it got shorter, didn't it? Which is exactly what this equation would have predicted too. If it slows down, wavelength has to go down, frequency stays the same. The only way to make this all consistent is, this beam had to change direction, so these angles are different from each other. Okay, so what is then the relationship between these two angles and how much the water slows down? Say maybe something to do with the index of refraction of water. Okay. That's called Snell's law. Snell's law. And it goes like that. Oh, well, I guess the answer is already given away. You may have noticed, I've got some new posters up here, some stuff we've been doing the last couple of days. One of these is Snell's law, hanging right about here. So it says that the index of refraction, I'll say N1, on one side, say for air, times the sine of the angle on that side, it's like the angle of incidence, is equal to N times sine of theta on the other side. N1 sine theta 1 equals N2 sine theta 2. Got angle of incidence, angle of refraction, it's the index of refraction of air, index of refraction of water. That's Snell's law. Okay, I kind of see that, right? Guess that? Oh, so now you have some way to quantify how much is something going to bend based on index of refraction or vice versa. Okay, so to do let's switch the screen over. Adjust my camera for switch the screen. Okay. And let's look at Snell's law play out for a bunch of different angles. Okay. Snell's law. Now this guy has very nicely a semicircle prism. And the reason this shape is really nice is because, here, zoom in about partway through this video, okay, is that there's only one place where the light actually bends, like it refracts. See, on my triangle shape, there's going to be two places, right? The place where it enters and then exits. But here, as long as he aims right at this central point, okay, the light does refract on the flat side. But then it emerges from like the center of a circle towards the perimeter of the circle, right, the circumference. On this curved side, it doesn't actually bend because it's always going to be perpendicular. So 90 degrees, well, 0 degrees from a normal line, 0 degrees. It won't actually bend a second time. Right, so let's take a look what we got. What angles are we measuring? See, with respect to this normal line, right? Just like reflection last couple of days. Okay. So see how the angle of incidence is, it's up to about, was that 40 degrees right there? Okay. And now it's up to 45 degrees. Okay. But what about the angle of refraction? Angle of refraction is about 28 degrees. You guys see that? It's not even 30 yet. Okay. Huh. So the angle of incidence is growing faster than the angle of refraction. Okay. No. Also, right about now, do you guys see some reflection starting? You guys see this very faint reflection line? So as he makes this angle, incident angle closer to 90 degrees, the reflection is going to get stronger and the refraction is going to get a little bit weaker, a little bit weaker. But you know what I'm thinking? I'm thinking, let's fast forward ahead a little bit. Can you guys predict what's going to happen? When this incident angle gets really close to 90 degrees, 90 degrees. Okay? Because the fact that the angle of refraction is not catching up as fast, isn't it going to kind of like peter out at some point, like hit some kind of hard limit? I wonder what that's going to look like. Let's get close to the end of this. There's 80 degrees for the angle of incidence. The refraction is really weak, but it's about 40 something. Here's 85 degrees. I should mean pause the video right there. That's about as far as we can go. Right. So at this 85 degree angle of incidence, it's almost all reflection. That reflection is getting really strong now. There's a tiny bit of refraction that's really weak, but you can just barely make it out. It looks about 40 something degrees. I'll call it maybe like 42 degrees. You guys see that? Okay. Huh. So if you were an ant crawling around on this paper and you were hanging around, say, the 20 degree mark, would you ever even be able to see the ray of light? No, because there will never be refraction in this zone over here. It'll never reach you. Okay? Huh. And this 42 degree angle, that has a name. It's called the critical angle. Let me show you what this would look like from the other point of view. You flip this whole thing around. So basically, same experiment. You just shines in the light from the other side. but the geometry is the same. So if you just saw the rays of light, it would be ambiguous as to whether you were shining top down or bottom up. Okay, same idea. Okay. But I like this setup because look at this refracted beam over here. Okay, see how that one's now racing ahead very quickly. Okay. It's getting towards 90 degrees and boom, like right there. Yes, pretty well flush to the surface. Okay. This angle went all the way to 90 degrees, but what angle is he shining it in? It's 42 degrees. Look at that, 42 degrees. You guys got it? Okay. And anything after that is going to be what's called total internal reflection. That's the name of this video. Total internal reflection. See this reflection now? Okay. Anything that goes beyond that, there's all reflection and no more refraction. It's all reflection. Okay. Right, so flip back to this page. A little bit. All right, we are ready for, well, almost ready for the lab. You know what? I wonder what the index of refraction was for his material. Okay. I wonder if it's the same as this or something different. Okay. We can actually figure it out based on that critical angle. So let's do a quick calculation. So on one side, say the side of air, index of refraction was 1, and that angle went to 90 degrees for that. That was the point where it went critical, right? I'm curious to know what is the index of refraction of that material, because I saw that the critical angle was about 42 degrees, right? Wouldn't that be true for that setup? Okay. And we can solve this really quickly with some algebra. Just take sine of 42 degrees, divide it down. Oh, what is sine of 90 degrees, by the way? It's equal to 1, exactly. So this is really 1 over sine of the critical angle, 42 degrees. It looks like his index of refraction was, it says 1.49, 1.49. So it's probably 1.5 is probably what it was. But 1.49 based on that critical angle. Okay, guess that. Oh, so there's a quick run of Snell's law to solve for something. Okay, let's apply Snell's law to some kind of lab setup. Okay, so double check. Does anybody not have this quarter page? You guys got this? Okay. It's got a table, bunch of rows. We're only going to do a couple of these rows, but we're going to measure some angles. So time out. Pause the recording. All right, so recording restarted. Let's take a look. Going to trace this out. Going to shine this laser through. We're going to watch this thing refract and try to make some measurements. Okay. So shine laser through. Find a pretty good place for refraction. It's left-handed, so I'll picture right-handed. Okay, I see this bead of light going here, and I see it refracting out here. That was also a bunch of reflection stuff going on. So let me do my very best to get the path this is going. So I see it going kind of this direction. Okay, follow that as close as I can, and it refracts kind of here. That looks pretty good, I think. It's pretty close. All right, we're gonna run with that. So I pick the pink ink to draw the top of this red laser. So went in about this angle or so. It emerged approximately like this, and in between it had to have done something kind of like this. Okay. Boing, boing, boing. Okay, guess that. Okay. So I've got 2 places where it refracts. We're going to measure each one of those, record it, and run Snell's law and see if we can figure out the index of refraction of this material. How much does this refract? How much does it slow down by? So I need some normal lines. Let me get a normal line here. Just like last few labs, I would normally have you guys do this yourselves, but trying to protect you guys from COVID. So I'm going to do this demo style, but just follow along with me. Whatever notes you want to write, and then when you guys turn in this page at the end of the day, I'll give you guys some points for this. Okay. Let's start with this one. We'll worry about the other one later, but I'll start with this pair of angles here. So here's my angle of incidence. Here's my angle of refraction. Okay. You guys have used a protractor for a few labs in the past in this class. You guys remember how this works? So I'm going to take this node, put it right on this point, zero out the normal line, and see where does the pink line sweep through. That is about 43 degrees right here. This is 43 degrees. Right? Or if you like, you could have zeroed out the ray and see where does the normal line sweep through. that's also 43 degrees. It's the same angle, no matter how you measure it. And what about this angle of refraction? Maybe I'll zero out the ray and see where's the normal line sweep through. That looks like 25. That's 25 degrees. Okay. So I've got my two angles, angle of incidence, angle of refraction. Okay. Let's run Snell's law. So in this way, I should have drawn this on the left side of the paper. I'm right-handed. Won't get my hand in the way of my notes. Should have planned that one out. So N1 sine theta 1 is equal to N2 sine theta 2. Okay. Well, we know we have the two angles. Okay. They're 43 degrees on your paper, 43 degrees and 25 degrees. I did make columns to take the sine of those, so why not? Let's do it. What sine of 43 degrees is 0.682. What sine of 25 degrees is 0.423. And the index of refraction of air that's on the side of the 43 degrees is equal to 1. So 1 times sine of 43 degrees is equal to index of refraction that we're solving for times sine of 25 degrees. I'm going to take sine of 25 degrees, divide it down. What is sine of 43 divided by sine of 25 degrees? That'd be 1.61. So index of refraction of this material says 1.61. Okay. Now that's one measurement. Having done this lab for so long, usually get an index of refraction in the ballpark of about 1.5. I wonder if this actually is the same material as you guys saw on the video. Sometimes a little more, sometimes a little less, but it's pretty close to that, isn't it? Okay. We can actually get a second reading based on this refraction right here. Let's do that. Now, I've got kind of a tiny triangle. There's going to be a lot of ink here, but that's okay. We're going to make this work. Okay. So I still need a normal line. Here, we'll take this bright blue to make the normal line. 90 degrees from here. Okay. Right, now, for this one, this would be the angle on the side of the air. And this would be the angle on the side of the glass, some kind of plastic or probably glass. Let's see what those are. This one is 50 degrees exactly. This is 50 degrees. And what's this guy over here? 33, about 33 degrees. And so that angle versus that angle. Right. Record those. So 50 degrees versus 33 degrees. Okay. What is sine of 50 degrees? That's 0.766. What is sine of 33 degrees? 0.545. All right. Let's run Snell's law for that pair of angles. So 1 times sine of 50 degrees. Okay. Now 1 pairs up with the 50 degrees because that's both on the side of the air, is equal to N2, this is pretty solid for it, times sine of 33 degrees. So what is sine of 50 degrees divided by sine of 33 degrees? That is, 1.41. Okay. Okay, remember I said this usually comes out to about 1.5, right? Well, one way we've measured is a tad above it. One way is a tad below that number. So one method we got, or one set pair of numbers, we got 1.61. Then another, we got 1.41. Okay. What I've been doing all day is just taking an average of those two. So let's do that. So the average of those would be, of course, 1.51. That's in between. Let's go with that, which is pretty well in line with what I usually get for this lab as well. Okay. Let's go there. Now there's another part of this lab, which is to figure out what is the critical angle associated with this type of material. Now, once you know the index of refraction, there should be some set critical angle that's paired with, and vice versa. If you know the critical angle, you can get index of refraction, which is kind of what we did for this piece here a few minutes back. Okay? So I want to do two different methods to get the critical angle. One way is going to be a calculation based on this index of refraction. We're going to say it's 1.51. And the other way is we're going to do a direct measurement, get an empirically measured value, okay? And we'll see how close this are. So I'm going to do this in a kind of a funny way, but just go with me on this. I'm going to set up an equation to solve it. Then before I solve it, I'll go get the empirical value, and then we'll go back and solve the rest of the equation and see how close do these two match. Okay? It's a pretty good way to do it. So Snell's law, n1 sine theta 1 equals n2 sine theta 2. Okay. You saw what we just sort of did something very similar a few minutes ago. So air times, now if it is the critical angle, that would be the point where it refracts out at exactly a 90-degree angle on the side of the air. So these two go together. That times that is equal to 1, by the way. It's all equal to 1. Equal to, now in this case, we're going to say we know what the index of refraction is. We're going to go with 1.51 because that's the average of our data, right? 1.51. Okay. And there is definitely some critical angle to make this all work out. Okay, guys see the setup? Okay. I bet some of you guys remember how to solve that particular equation, which we haven't done one exactly like that today, but back in the fall we did, sort of. Okay. How do you extract this angle out of the sine? Okay. But before I solve the rest of that, let's do the empirical way again. And the empirical way is just a direct measurement. Trace this. Where's my laser? Okay, I haven't walked in. Did I? Oh, thank you. Thank you so much. That was the answer. So let's see. Okay. I want to get some kind of refraction where it goes like it emerges like flush 90 degrees to a normal line. Come on. Okay. So see this ray light right here? Okay. If I rotate this laser, switch my hands. All right. Right about there. See, it goes like pretty close to flush to the surface. Okay, and then everything after that would be total internal reflection. Okay. This is tricky because it, remember, refracts twice. So I'm going to do my best to figure out exactly the angle I'm holding it at, make this all happen. Okay. So let's back a little bit. Okay, so right about, it's really close to right in here. Okay, now rotate this back a little bit. Right, that was sort of verging from point, right? Okay, it's hard to get this exactly. About there, it's about. Okay. I'm making a kind of an educated guess on the point that's reflecting on. I think it's about here. Okay, this may not be the most accurate that we're doing this today, but here's sort of my best attempt to get the path of that laser light. Yeah, limited time to try to figure this out. I want something about like this goes about, okay, where this point right here, get this, okay, get a normal line. I better measure out 90 degrees. So hold this flush, 90 degrees, point. Okay, looking at, here's my normal line. Okay, this angle is really close to 90 degrees. I'm going to call that about 90 degrees. Okay? And this angle should represent approximately the critical angle. So extrapolate this normal line back. Get a direct measurement. Okay, so here's the direct measurement of the critical angle. Okay. It is, I'm looking at 48 degrees. This is 48 degrees. Right, so one method of getting the critical angle, the direct measurement, was 48 degrees. Okay. But we're going to do this other method of calculation. Now I've set it up ahead of time, so can't cheat myself, can't adjust my measurement because I don't know what this is going to work out to be yet. But what is, okay, this is all equal to 1 divided by 1.51 is equal to 0.662. It's equal to sine of the critical angle. Okay. Right, now, who remembers from last semester, how do you extract this angle algebraically? You have to do what to both sides? Take the, how do you undo a sine? Inverse sine. You guys know that? Like, how do you undo a square root? Well, you square both sides. How do you undo a sine? You take the inverse sine. Okay, so we're going to do inverse sine of 0.662. That's equal to the critical angle. Okay. So what is inverse sine? I'll say the answer, get more decimal place. 41.47. So that rounds down to about 41 degrees. Theta critical should have been about 41 degrees. Okay. And our measured value was 48. Calculated value should have been 41 based on the index of refraction. Yeah, those two are pretty close to each other. So either, I don't know why I wrote it like that, either 48 degrees, that's empirical, or 41 degrees calculated based on index of refraction. A few different methods. They're both the same, kind of about that ballpark. Right. Guys good there? So do this, keep this quarter page out and about the last minute of the class, pop that in the grade tray, and then I'll give you guys some points in the grade book for that. But last few minutes of class here, I want to get the next activity going. I want to look at refracting lenses. So put this, yeah, let's go. Refracting lenses. I want to make some ray diagrams. You guys remember we did ray diagrams for mirrors, like concave and convex mirrors. Okay. So now we're going to do lenses where the light actually passes through. This is going to be the foundation of technology like wearing glasses or contacts. This is going to be eventually how you can build microscopes and telescopes. Magnifying glass. Actually, one of these examples I have lined up that actually is going to represent a magnifying glass. How does that work? Lenses. How do they work? We're going to do 4 examples. So 2 on the front, 2 on the back. Okay. Well, if you need paper, that you have, put a stack right here. So help yourself, need some paper. Pretty good. All right, so first one is going to be a converging lens. So draw it like this. This is a converging lens. Okay. It's a refracting lens. And remember yesterday and the day before, we needed some focal points for those mirrors. Now, this is obviously not a mirror, this is a lens, okay? But still need some focal points. So maybe I'll put a focal point, maybe 5 centimeters this way and also 5 centimeters this way. Now, why did I draw 2 focal points? Let me think about it. The light might be passing left to right, or it might be passing right to left. It could refract either way, and this is symmetrical. Okay, so that's why we got a couple focal points. Okay. Now this first picture, I'm going to put an object that's within the focal distance. So here's my object. Right. See, here's the focal distance, the focal length. Right. Here's the object is within that focal length. Okay. If you do that, I'll tell you what the outcome is going to be even before we do the ray diagram. Okay. This is going to be a magnifying glass. And your perspective is like you're over here, there's like an eyeball looking this way. Right, looking to the left. Right. What would the image be? Because here's the object, we're trying to magnify it, we're holding up this magnifying glass. Okay. I hope this guy's going to see something that's larger than the original object. I mean, that's the point of a magnifying glass, right? Right, so here we go. Remember, there's a billion rays bouncing all different ways, but you only need a couple of rays to figure out where the image is going to be. So let's do similar to what we did yesterday. There's going to be one ray going parallel. It's right in the top of his head. Okay, now where's that ray going to go? Well, it's going to refract technically a couple of times. Once here, it's going to refract kind of this way, and then second time right here. But the end result is going to, the ray of light is going to be directed through this focal point. Okay? So any light rays that come in parallel to some ground are going to be refracted through the focal point. Okay? Or vice versa, you can actually have a ray light that goes this way, boing. Okay? Now, the person perceiving this ray of light coming this direction, seeing this light ray, would perceive if it's coming from back here, like you could extrapolate backwards. See that? Extrapolate backwards. Yeah. Okay. That's what's for. Okay, now the next thing we're going to do is unique to lenses. We're about to draw a light array that we did not do for reflection. This is only for refraction. We're going to go from the top of this guy's head through the center of the lens. There's a ray that does something like this, pretty well travels in a straight line. Okay. Maybe it refracts a little bit here and a little bit here, but the net effect is it pretty well goes in a straight line. I got this to barely fit on my paper. Okay. See how these two are going to converge right at this point? That is going to mark out the top of this guy's head. Oh, whoops, it actually did go off the paper a little bit. Oops. Okay. That's going to be where the top of this guy's head is. So, just a little bit, pretty much like right here. Those two converge. And that is going to be your image. Look at that. It did magnify, didn't it? Right? Got a magnifying glass for it. And if you take the ratio of these two, this divided by this, you get how much it magnified by. Right? That's the definition of magnification, the ratio of these two heights. Let's say the same magnifying glass, same converging lens. Okay. Got put the focal points in about the same spot. About here, focal. Okay. But what if I draw the object outside the focal distance? What's going to happen? Maybe I'll put the object kind of over here. Okay. Where's this going to show up? Okay, so similar story, the guy's like looking this way. This would be equivalent to if you take the magnifying glass and you move it too far away from what you're trying to magnify. Is it still going to magnify, or is it going to do something kind of weird? Well, let's do the same method that we just did. Ray of light, skirt top of his head, parallel to the ground. It's going to refract through that focal point. Okay. You could have chopped it backwards, but it's not going to be applicable to this one. Okay. Then we're going to go from the top of his head through the center of the lens, just like we did before. And oh, these rays are going to converge over on the other side. It's going to create an inverted image. Look at that. Image is going to show up here. Okay? So if you hold a magnifying glass too far away from it, what you're trying to look at, you might see kind of a hazy, floating, inverted image. It looks like a real image kind of hovering in front, like that. There's actually a third ray you could follow that would confirm the story. If you go from the top of his head through this focal point, take that to this lens, and then goes refract, and then refracts parallel to the ground again. Oh, look, it all matches up, doesn't it? You did that too. Just to confirm your work. Okay. Thanks for that. Okay, so we've got the object inside the focal distance and outside the focal distance. What would happen if you put the object right on top of the focal point? That's the next one we'll do. Right on top of the focal point. Actually, I better wrap up class because there's a run to the bell. So we're going to do that, and then the last one we'll do is actually going to be a diverging lens. We'll do a diverging. Okay? But we're going to have to save both of these for tomorrow. So hang tight on those. And last minute of class here, throw your quarter page lab in the ray tray. As long as you did it and got the numbers where they go, then I will give you some points in the grade book. So continue this adventure tomorrow.